Hello and welcome to another creative coding video. Today we're going to be returning to the familiar topic, I guess, of rendering the Mandelbrot and Julia fractals, but we're going to take it a little bit further in a way that I think a lot of tutorials and guides don't, and it's to solve a specific problem. We have done a previous video on the basic method for rendering the Mandelbrot set and the Julia set, so do go back and look at that if you need a refresher or you want to take things a little bit slowly. But the point of today's video is to introduce a new method for drawing details which are missed by the standard method. So on the screen here you can see a plot, a rendering of the famous Mandelbrot set, and we know that the Mandelbrot set, with all its detail and intricate forms around it, it's actually one connected set, and what we've seen here is blobs, details, parts of the Mandelbrot set which appear to be disconnected. There's things on the screen that look like dirt or dust, but they're actually parts of the Mandelbrot set, and they appear disconnected, and that's because the structure that connects them is so fine that our rendering method misses them. A simple way to think about that is that the pixels are too coarse, but there is a deeper problem as well, which we'll go into. So that's the motivation for today, and we will be producing some really interesting results, some nice plots. So I hope you'll come along for the journey. So let's do a bit of a revision. So as I say, there is a previous video going through this properly, but just as a quick reminder, what is the Mandelbrot and Julia set? Well, the basic idea is that we have an iterated function. Let's think of a simple one like x squared, and by iteration we mean we take a value of x, and then we square it, and that becomes the next value of x, and we keep repeating that and watching what happens to x. So if I start x as x naught, the first one is 2, if I square it, it becomes 4, if I square it, it becomes 16, square it, 2, 5, 6, and it just gets bigger and bigger. If I start at 0.5, then that becomes a quarter, that becomes a 16th, and 1 over 256, and so on. So that becomes smaller. If I start at 1, then square of 1 is 1, 1, 1. So you can see already that some starting values result in the sequence getting bigger and bigger and bigger and exploding. Some starting numbers get smaller and smaller and smaller, and some just don't change. So that's the basic idea of a function that's iterated, and the idea of us watching what happens to that sequence. You can think of other functions that you can try. You can try simple ones like x maps to minus x, so that will just flip-flop. So 2 will become minus 2, becomes plus 2, minus 2, and so on. So that's not that interesting. What's much more interesting, and this is the surprise as it were with the Mandelbrot and Julia fractals, is that if we use complex numbers instead of normal real numbers, we use a formula which is x squared plus c, or z, just to distinguish the fact that they're complex. If we do this and watch which values go higher and which go smaller and which kind of perhaps don't do anything, if we plot, and remember complex numbers are two-dimensional, so it's not like a linear line like the real number line, like 0, 1, 2, and so on, -1, -2. Complex numbers are two-dimensional. They have a real part and an imaginary part, so we can visualize them on a surface, a two-dimensional plane. So you can have, say, a number here, a complex number, which is 3 plus 2i. That's the convention. So 3 along the real axis and 2 along the imaginary axis, 2i. So that's there. And if we take that and if we apply z squared plus c, so if we start z with z0 is 0 and c is this number here that we're testing, that number, say 3 plus 2i, and if we keep repeating it, we might find that the numbers, they kind of rotate definitely, but they might kind of escape and get bigger and bigger and bigger in terms of their distance from the origin. Other points that we test might get smaller. Others might just kind of rotate around and not really get much bigger or smaller. And that distinction is what is behind the rendering of the Mandelbrot and Julia fractals. So let's just remind ourselves what the difference is. This is all on the blog, by the way, if you don't like my handwriting. So for the Mandelbrot set and the Julia sets, Julia, Mandelbrot, with the formula that's iterated is the same, but the difference is how we use z and c, in particular z0. So z0 and c. So for the Mandelbrot set, z0 starts at 0 and c is a point that's being tested. So test point. So that's the point on the plane that we're testing, and that's just what we've illustrated just now. With the Julia sets, we have z0 being the point that we're testing, and c is fixed. So we just choose a c, and that is the c for that Julia set. So different c's will generate different Julia sets. And the surprising thing is that if you plot if you take the kind of complex plane, and if you plot those points, if you colour in a dark colour, those points which don't diverge, for the Mandelbrot set, the object looks a little bit like that one we just saw, with lots of details. And that's quite surprising. You know, you might expect a circle or an oval or a square or a diamond shape or a rectangle, but we have that very infinitely detailed Mandelbrot set, and similar for the Julia sets as well. We have some really interesting shapes. So that's just a quick overview. As I say, rushed that because just wanted to remind ourselves what the Mandelbrot and Julia sets are. So let's talk about the problem we're trying to solve. So very simplistically, if I have a computer screen like this, and I've got some pixels, these are huge pixels, but I'm just drawing them just to illustrate the idea. And then going down, 1, 2, 3, 4, maybe add another one there. So these are pixels that we are rendering, that computer screens are made of. So already you can see that the method by which we draw is limited. You know, the pixels of a certain size, so they can't show infinite detail. More to the point, when we test a point, remember those test points that we said for the Mandelbrot and Julia sets, we often pick the center of these pixels and the value that we calculate, what is kind of z0 there. So it's actually a grid that we're testing. So we're not testing, let me just draw a few more of these. So what we end up testing is a grid of points which have between them a distance. So a point that, say, here is not tested, a point here isn't tested, a point here isn't tested, a point here isn't tested. It's just that point there. Now, depending on how you calculate, you might actually be doing like the bottom left corner instead of the center, but the idea is still the same, that by having a grid of pixels and by testing 1 point per pixel, we're actually not seeing what's going on here. All we're doing is testing that point, and even testing that point is limited because, as you know, if we're testing to see if a point kind of escapes, we can't test it forever. We can't run those iterations forever, so we have a finite number of iterations we can test for, and in that say we've got 32, or even say 1024, or even 4096, we can test it for a long time. We can run lots of iterations, but the orbit of Z might not get very large. It might take longer to diverge, so there's always an imperfection there. It's good enough, for most renders. It's fine. If a point has already diverged and is huge by the time we've got to say within 32 iterations, then that's fine. And mathematically, we have escape conditions that we can prove that if for the Mandelbrot set, if the magnitude of Z becomes more than 2, then it will definitely diverge. And in the links on the blog, there is a proof that you can see. For the Julia sets, the escape condition is slightly more involved. Often people just use this one and it's fine, but strictly speaking, it's Z is more than 2 and Z is more than the magnitude of C for that Julia set. But it's not going to make a huge difference. And other, if you look at software implementations, a lot of people just increase that to 4 just to be sure, and that's fine. So we already have an imperfect way of testing a point. That's problem number 1. And then problem number 2, the one we're interested in today, is that the points that are tested will miss detail. Let's draw some fractals. Let's see, what color shall we use? Let's use pink. So imagine there's some really interesting detail that goes like that. Some interesting kind of forms that are really swirly and curly, like that. Now you can see here that maybe we'll catch that one, but all this detail we won't catch. All this detail we won't catch because we're only testing that point there. So it's almost the detail is sub-pixel. So what's the solution? We need a new method. This method, the simple one, which is quite powerful, quite good. It just won't cope with this level of detail, and this becomes a problem, particularly when we do deep zooms, where there is fine detail to be seen, if we can see it. And the new method relies on a different idea. And the idea is that we are testing not whether a point is in or outside the Mandelbrot set, but we're testing how close it is to the Mandelbrot set. So that's very different. Let me draw a picture just to explain that. So if this is a part of the Mandelbrot set and there's some interesting kind of details, colour that in. So if we have a pixel like that, we may or may not hit that point. This one here, got another pixel here, and this one will miss it, say. So that one hits, but that one misses. Now, instead of testing whether the point at the middle of that pixel is in the Mandelbrot set, as in the point doesn't diverge, instead of doing that, so 1 is point in set, whether it's the Mandelbrot or Julia set, we ask a different question. We say, is point close to set? That solves that problem of having a grid. It means that if our pixel is here and that's the center of the pixel, we can detect if we are close to the Mandelbrot set or the Julia set. So this, it means we don't need to hit the actual set itself. You know, if the points are close, then we'll kind of come up with some measure to say how close we are. So that's brilliant, because it means that we don't need to be hitting the set itself. If we're close, then we can detect that. So that's a fundamentally different approach. So instead of asking, is the point in the set? And as we've seen, the weakness of that is if the point is close to some detail but misses it, then we've missed it. Whereas if we ask, is it close to, then we won't miss the detail. We're either very close or medium close or not very close or quite far. And the beauty of this is that it doesn't matter which direction we're kind of looking at the Mandelbrot set in. So if that's the Mandelbrot set, if that's the point we're testing and we're asking how close are we, that's the distance. And if it's here, that's the kind of distance, the direction. So it doesn't really matter if we don't need to ask, are we horizontally close or vertically close? We just, are we close? So that's quite a fundamental shift. That's quite powerful. Let me show some other pictures just to illustrate that. So you've seen the Mandelbrot set many times, and one of the many kind of common colorings is to color the outside according to how fast the points there reach the escape criteria, how fast they kind of diverge. The inside is usually colored black or white, because it's inside the Mandelbrot set. The points don't escape. So a point here will escape quickly. A point here will escape moderately quickly. Points very close will take a lot longer. So that's how we decide the coloring, and that's what we did in the previous video. So you have a look if you need to remind yourselves. Now, if you look at this as a kind of topographical map, these regions are all the same in terms of their escape speed, and the lines are what separate them. So this might take 10 iterations, this might take 2 iterations, this might take 20 iterations, and the closer we get, the more iterations we need. But lines being close together on a topographical map mean that the gradient is higher. You've seen kind of maps of terrain like land, valleys and mountains and hills. If the ISO lines are close together, then the gradient, the slope, is quite steep. It's either a huge rise or a huge drop. And if they are spread out, then the difference is gentler. You can see that. So from here to here, it might be 10 iterations, 12 iterations, and that's a short distance to jump to. Whereas here, it's 10, 24 and 26. It takes longer to get an increase of 2. So that's the intuition. So what we are going to do, and this is the key to the method, is to use the gradient as a way of estimating how close we are to the Mandelbrot set or the Julia sets. So again, that's the powerful point there. It's the second important point to take away. Number one was, instead of asking, is the point in the set or outside the set, does it diverge? Instead of asking, is the point, we're asking, how close is the point? And we answer the question, how close, by using the gradient. If you've seen surface like height fields or fractal landscapes made from these, you'll have seen that the gradient drops quickly as we are close, and then it kind of shallows out, as it were, as we go further away. So it's called distance estimation method, or DEM. That's, if you Google it, that's what you'll be looking for. But I think that's not a great name, because it's actually gradient that we're using. I wish it was called the gradient method or distance estimation by gradient, but that might make it too long. So Before we dive into coding, I'm going to try and justify the algorithm, and just do a little bit of maths. Skip it if you're not interested in the maths, but I thought it'd be useful to do that. Right, so let's set out some basics before we work out the algorithm for working out the gradients. So we know that between the Julia set and the Mandelbrot set, there are some differences. With the Julia set, we have Z0 as the test point, and C is fixed. With the Mandelbrot set, it's the other way around. C is the test point, and Z0 is fixed at 0. It starts at 0. And the normal calculation that we do is the next Z, n plus 1, is calculated from Zn squared plus C. It's the same between the Julia and Mandelbrot sets. Zn plus 1 equals Zn squared plus C. By the way, this is all online if you want to read it, if you can't read my handwriting. I just thought it'd be good to talk through it. So what we have at each iteration is the old Z being used to calculate the new Z there. What about the gradient? How do we do that? It sounds like a really complicated, difficult thing to do that doesn't fit the simplicity of this. Turns out that it does, and it turns out the maths isn't that difficult either. So let's do it. So let's differentiate this and see where it takes us. Let me pick a different colour. So what are we differentiating with respect to? With the Julia set, it's Z0 that varies, and C is fixed. So we're differentiating with respect to Z0. Let me pick a slightly thinner brush just to write more detail. So Zn plus 1 equals that differentiated, and with the chain rule that gives us 2 times Zn times d by d Z0 of Zn plus this differentiated. Now C is fixed, so d by d Z0 of C is 0. So it's just that might look a bit horrible. We'll see it's actually useful. Let's write this down in a slightly different way, more concise way. So Zn plus 1, the next gradient, equals 2 times Zn times Zn previous gradient. So you can see how the old gradient is being used to calculate the new gradient, and this fits in with our iterations. So when we do an iteration, we calculate the next Z, but we also calculate the next gradient. So that's nice, that's brilliant, it fits nicely. Let's do the same here. Let's do the calculation here. What does that look like? So here, what are we differentiating with respect to? C is the one that's varying, and Z0 is fixed. So it's with respect to C, d by dc of Zn plus 1 equals 2, this is the chain rule, times Zn times d by dc of Zn plus d by dc of C, which is 1. So there's a slight difference now. Here the expression is Zn plus 1 gradient equals 2 times Zn times Zn gradient plus 1. So that one's got a plus 1 and this one doesn't. And again, this fits nicely into our iteration because we're using the old gradient to work out the new one. Now one question remains is, what are the initial values? Because if we're doing an iteration, we have to start seed with the seed value and initial value. We know what the ones for Z are, Z0. What is it for and C here? What is it for the initial gradient? Well, the initial gradient happens at Z0. So at Z0 we're asking what's the gradient d by dz0 of Z0, and that's 1. So that's the seed value for the gradient. So Z0 gradient equals 1. And it's different here. Here we're asking dc of Z0, and remember Z0 is fixed anyway, so that's 0. So the seed value here, Z0 gradient, is 0. Sometimes you'll find online people get this wrong, or the wrong way around, or they just set it both to 0 or both to 1. But this is the explanation of why they are different. It explains why the actual iteration formula is different and why the seed values are different. So that's an explanation of the calculations. I hope you did find that interesting, or if you were curious as to why people seem to be using these formulas, but there didn't seem to be an explanation. Here it is. And as I say, it's on the blog as well, written out more thoughtfully, so you can follow that if you found this one difficult. So let's have a go at coding. And what I'm going to do with the coding is first implement it with the very simple rendering method of black and white, is it in or out? And then I'm going to use the standard method of colouring the outside according to escape speed and show its limitations, and then we'll use this method. The code, I won't start it all from scratch. The code is online, GitHub, if you want to kind of have a look yourselves. And as I said, the previous video on Mandelbrot and Julia sets explains how to write the code for it. So we won't kind of waste time doing that, but we'll just focus on what's new today. So this is a Julia generator, Julia set. As usual, we import, let me increase the pixel size, the writing size, so you can see. Hopefully you can see that. So we import NumPy because we use arrays, and plotting library so we can visualize it. Set some initial variables, so we're going to have a resolution of 1024 by 1024. That's our pixel grid. So it's 1024 width, 1024 height, so that's about 1,000,000 pixels. Quite a lot of work to do. With the Julia sets, the standard view of the whole thing is usually from minus to minus 2i and a size of 4. That means we haven't zoomed in. And I'm going to start off with just a few iterations because I'm going to choose a deliberately chosen Julia set which is difficult to render to see, just to illustrate the kind of the point. So 32 iterations means we get a rough and ready inaccurate view, but it's enough to see it. And the value of C here is this one, minus 0.8 plus 0.16i. Remember, each Julia set is defined by a specific value of C, and this one defines this Julia set. And while we're here, just for efficiency, we might as well calculate the absolute value of C, because we'll use it later. Some things, if you can calculate them outside of a loop, it's more efficient than repeatedly calculate them inside a loop. We're creating an empty array from NumPy, which is the size resolution by resolution, initially filled with 255, which is white, as in maximum light, and 0 would be black, so 0 black, 1 to 8 would be a mid-grey, 255 would be white. So that's the empty white image that we first create. And then we visit every pixel, so for X in range resolution, Y in range resolution, and then we calculate the initial Z. So Z is the bottom left, which is the bottom left of that view, this one. And then some calculations with the size and the value of X and Y, the pixel values, the pixel kind of which pixel we're on, to calculate the Z. I won't go into that now. You can look at the other video if you interested in that, or if it causes enough problems, do comment on the video and I'll explain it. Essentially, it's converting the pixel position to a z naught. And then we go into iterations. So for a maximum number of iterations, which we set up here, 32, we set ourselves 32 as a maximum number of iterations, and we repeatedly calculate, repeatedly iterate that formula. So z squared plus c becomes a new z, z squared plus c becomes a new z. We keep doing that, and while we're doing that, we're calculating the absolute value. That's the distance from the origin, or the size of that complex number. And for Mandelbrot sets, the escape criteria is just that, and for Julia sets, properly speaking, it's this. Is the absolute value of z more than the absolute value of c as well? A lot of people miss this out. Fine, just for complete accuracy, that's there. Again, there's a blog talking about the derivation of these two escape criteria, the one for the Mandelbrot set and the Julia set, if you're interested. So if we reach the escape criteria, we break from the loop, and then we use the iteration count. If we reach the maximum, that means for 32 iterations, and we didn't hit the escape criteria, that means we have to conclude that the point doesn't escape. It's imperfect, I know, but we can't run the iterations an infinite number of times. If, however, we did reach the escape criteria, then the iteration count would be less than the maximum iterations. So then we don't colour it. We're only colouring the inside of the set and making it black, so 0. So instead of 255, which is white, we're making it black. And then we're rendering the point. Now, I won't go into what all these matplot instructions do in detail. Matplotlib is honestly, it's a pain sometimes, but often most people, even experienced people, just Google and find the right code to achieve what they want. But broadly, we creating a figure, setting a size, removing the ticks on the X and Y axis, doing the border a grey colour just so it looks nice. We're plotting the image after we filled in some points which might be black. We're doing it a grayscale, and we're making the origin of the lower left rather than the top left. And I'm also writing on the image the value of C, so it's just stamping the image with the value of C. So if I run that, hopefully it doesn't take too long because I'm only doing 32 iterations, so that's quite quick. This is done on Google's Colab, by the way, so that's there. And that's the Julia set coloured in black and white for that value of C. Now it looks a bit blobby, and that's because the number of iterations were low, so it's inaccurate. But I'm showing you just to show you it's there. So a reminder, if the pixel is black, it's because we couldn't detect it escaping. It didn't reach the escape criteria. That's the inside of the Julia set. Let's increase the iterations to say 1 to 8. I just run that again just to make it more accurate. But making it more accurate means the detail becomes finer. And you can see, yes, there is some detail there, and it looks disconnected actually. So some Julia sets are one single piece, and some are lots of different disconnected pieces, unlike the Mandelbrot set. And you can see the detail is now starting to fragment. So you can already start to see that if we increase the number of iterations, the accuracy, this might just disappear into nothingness. 256. Right, so now it's almost vanished. As we've increased our accuracy and determined that more and more points do actually escape and are coloured white, the ones that are left become harder and harder to see. So I'm illustrating the challenge. So one standard way of dealing with this is to use colouring for escape time, and that means colouring the outside according to how fast it escapes, and that hopefully shows patterns and structure, which gives us a hint of what this looks like. So just before I do that, I'm going to zoom in just to increase the challenge a little bit. So I'm going to say the bottom left of the viewport is at 0 and minus 0.5, and our scale is now 1. So we're not zooming in a lot, we're zooming in a little bit. So let's see what that looks like just before we try a different rendering method. Right, so this is the view that we're going to stick with, and you can see that, yeah, there's some interesting detail here. There's some swirls there, there's some swirls there, but it's hard to make out in a kind of really, it's unsatisfactory, this view. We can tell there's something there, but the method just doesn't reveal the detail, because the structures, as we said earlier, are too fine to hit the points that we test. So let's change the rendering method. So what we're going to do is, instead of only colouring the points that don't escape, we're going to say colour pixel according to divergence. Speed, say. So we're going to choose a pixel point, y comma x, that's how NumPy works, and we're going to color it based on the iteration count at the point it exited the loop. So if I say max iterations, max iter minus iteration count, what does that give us? So if the iteration count was the maximum, that will be 0. It's maximum when we haven't detected divergence. So we colour it black. So that minus that is 0, which is nice because that'll be black. But if it's anywhere else, let's say halfway through the maximum iterations, we detected divergence, then this would be half the maximum iterations. So we can use that number to colour, but we want to scale it to our range, which is 255. In fact, we can just experiment with some scalings. So just choose that. Actually, no, I'm gonna justify that. So if the iteration count is the maximum iteration, then we haven't detected divergence, and we want that to be 0, which is great. If it's anything else, we're going to colour it, but what I'm going to do, I'm going to take the modulo, so we have a banding. So this will then go from 0, 1, 2, 3, 4, 5 up to 15 and start again. So 0 to 15, 0 to 15, 0 to 15. That's what the modulo does. So it's the remainder after dividing by 16. So that will go from 0 to 15. So if the maximum is 15, we can divide that by 15 and scale up to 255. So that's the scaling that we're going to do. So let's try running that. Run all that code. Yep. Hopefully it doesn't take too long. Right. So that was the dusty image, and now we've coloured in the exterior, and you can see it cycles 0 to 15, 0 to 15 around in that region. So it does reveal some structure. We can see there's something here going on, but it's empty. But it does highlight the actual Julia set structure itself, which is a massive improvement. That's great. But it is a little overwhelming, actually. We can almost see the Julia set almost as an absence of these broad kind of coloured regions. So it's an improvement. Not amazing, but it's an improvement. Let me compare the two side by side. So these are the exact same Julia set in the same zoom location. This was coloured using the black and white method. Is it in or out of the set? This is using the escape time. And yep, you can see more of the detail brought out. So it's an improvement. But it's not ideal, I think. I think we can do better than that. So we will see what the gradient method gives us. But just before I do that, I'm going to show you the same kind of comparison, but for the Mandelbrot set. So this is a zoom into a region of the Mandelbrot set, and you can see there are lots of little mini Mandelbrots, as you would expect, lots of little ones. And we know they should be connected, and we know there should be structure around here as well. The same with this escape time colouring. Shows a dramatic change in what we can see. So yes, there is this blob here, and there are some blobs, but we can see there's a radial thing going on here, which is almost absent here. We just couldn't detect it. So this goes to emphasize that point, that the standard method misses a lot of detail, and this almost shows it in a by absence indirectly. It shows the outside regions, the dynamics of the divergent region, which kind of in some ways indirectly shows the structure of the non-divergent region. So that's with the Mandelbrot zoom. So I was going to justify that calculation for colour, and skip this if you're already comfortable with it, but just in case you're not. So we are iterating up to a maximum number of iterations. Let's say that's 32 or 64 or something. If we, and as we go through the iterations, we have a count. If by the end of that testing cycle, we've done all the iterations and we've come out and the escape criteria have not been met, that means we haven't detected divergence. So we think the point is inside the set. So we think it's inside. And that count would be the same value as that, because we start 0 and we count along. So count is the maximum, and we haven't detected divergence, so the point is inside. If, however, along that journey we do detect an escape criteria, as in it's definitely going to diverge, it might be early, it might be late, it might be halfway through, then count won't be the maximum. It might be, say, 10 out of 32 or 16 out of 32 or 29 out of 32, but it means that we've detected divergence before we got to the end of the testing cycles. And here, because it's divergent, it's outside the Mandelbrot or Julia sets. So that's in, out. Now we use this count and this max value, we calculate a colour from that. So if I say max minus count, in this case it'll be 0. So max minus count equals 0, because the count has reached the maximum, and 0 is nicely black in most colour schemes, so that's the colour that black. If it's not reached it, this will be a non-zero value. Let's just say it's say that's 32 and that's 16, say, just to illustrate the point. We want to use that 16 to do some calculation with and come up with a range 0 to 255 for the colours. So 0 black, 255 white. And by the way, because I'm doing black and white or grayscale deliberately, that's why I'm doing this. You can choose to modify it and have more interesting colours, as we did in the last video. So this will go from 0 to 32 is the range here, but we want 0 to 255. We could scale it. We could say divided by max times 255. That will give us 16 out of 32 times 255, 128, which is halfway along, which is fine. But if I wanted to do a cycling, I can take a modulo, remainder after division, say divided by If I did 3, that would give me values of 0, 1 and 2, and then 0, 1 and 2. It cycles. So I don't get a 3, I just get 0, 1, 2, 0, 1, 2. If it's a 2, I would get 0, 1, 0, 1, 0, 1. So if I do %16, I get 0 to 15. So that's why I divide by 15 and multiply by 255 to get it into that range. So in that range, it'll go from 0 all the way up to 15, 0 to 15, but then when scaled up, it'll go 0 to 255, 0 to 255. That's the justification. Great. So now let's apply the gradient method. I call it the gradient method, the distance estimation method. So let's talk through some of the code. So keep the resolution the same. Keep that viewport. I'm going to increase the accuracy to 4096, which will take a lot longer to calculate, but I'll chop it out of the video. We are visiting every pixel as usual. Our Z0 is calculated as usual, but we also set the initial gradient, let's call it dz, and for the Julia sets it was 1. It's a complex value because it'll be wrong to just set it as a real value because we're working in the complex plane. So although the initial value is 1, which is just real, it might get updated to another complex value. And remember, for the Mandelbrot set, that's different. That's 0 for the Mandelbrot set. But for Julia sets, the initial value is 1. That's great. In the iteration loop then, we do calculate z as usual, but let's also calculate the next gradient. dz, the new one, is the old one of 2 times z times the previous gradient. That's the new one then. It's as simple as that. And remember, with the Mandelbrot set we added 1, but we're not doing that here. And just for simplicity, I'm just going to increase that to 4 as a rough and ready escape criteria. You can do it the more accurate way, but this works fine. There is another reason for increasing this beyond 2, and that's just to allow the gradient to develop a little bit. If we kind of bail out too soon, the gradient won't have developed. So some people might set that higher to 8 or something. It doesn't need to be too high, but setting it higher than 2 allows the gradient to develop. And then if the escape criteria is met, we break, and then we then use the gradient to calculate a distance estimate. Now I'm going to write an expression here which is based on some mathematics, which I won't explain here, but there's links to on the blog if you want to find out more. But the most important point is that whatever I type, if I divide by the absolute value of the gradient, that's the important factor. The smaller the gradient, or its absolute value, the higher the distance, or the higher the gradient, the shorter the distance, the closer to the set. And this stuff is just scaling. And I could just leave it, but I'm just going to follow what the papers have done. So it's the absolute value of z times 2 times the log of the absolute value of z. That's just the scaling. So again, if I didn't do that, it wouldn't alter the fundamentals, but I'm just following it for completeness. So let's just repeat what we've done. We've iterated the gradient after setting it initially, and then by the time we end the iterations, either by breaking out because we've detected divergence, or we haven't and we've reached the end of the maximum iterations, we then have a gradient at the end of all that, and then we use it to estimate the distance estimate, and it's an inverse relationship The smaller the gradient, the larger the distance. The higher the gradient, the smaller the distance, the closer we are. Then if I colour it, I'm going to colour it a different way. I'm going to use the tan H function. Now tan H, the hyperbolic tangent, takes any value and squishes it into the range 0 to 1. So I'm going to take the distance estimate and I'm going to scale that again, and this is just through experience really. Times the resolution divided by the size. I found that combination works. So if the size, the more I zoom in, that affects the scaling a little bit, as does the resolution. So that needs to be NP from the NumPy library. You can probably get it from the maths library. So we're just using the distance estimate, squishing it into 0 to 1 range, and then scaling that up to 255. So let's run that. Remember the previous one looked like this. Now this will take a little longer, so I'll run it and then clip it out of the video. Right, looks like it's done something. There you go. Now isn't that amazing? Look at the detail. That is a massive improvement, isn't it? So all those points that are dark are coloured dark, the pixels are coloured dark, because they are close to the actual structure of the Julia set. They're close to the edge of it. And look at the detail that's emerged. Isn't that amazing? That was just almost impossible to consider that with the other method. That's amazing. I'm actually genuinely kind of impressed. And all from that theory of switching the question from is the point in the set or outside to how close are we? A different question. Let's do a kind of side-by-side comparison. So that's the three compared. The black and white method, is it in or out? The escape time colouring, and then using this distance estimation by gradient method. It's the exact same Julia set, exact same zoom, and we were justified, weren't we? There is some really interesting swirly detail, but we've never thought just by looking at this that we would see all those paisley type curls on that, and it's only hinted at here. It's not really clear. So that's the method. When I first came across it, I thought this is going to be really difficult, but having looked into it, the concepts, the kind of intuition is really nice and simple. How close are we to the edge of the set? We use a gradient to estimate that, which is ingenious really, and the rest is just scaling and colouring. Let's also look at that Mandelbrot zoom with the three side by side. There you go. So this is a zoom, and with the black and white method, the in or out, we can see that there are little mini Mandelbrot blobs. And we know we can't see the connections there, but we know mathematically the Mandelbrot set is just one set all connected. With the escape time colouring, yeah, we can see that there is something going on here, but it's almost indirectly showing the detail because we're showing only the exterior dynamics. And this is the gradient method, and look at that detail. It's amazing, isn't it? Let's see if I can zoom in. Look at that, amazing. And that's what's possible with this gradient method. So I hope you enjoyed that. I hope it's kind of demystified it a little bit. I was actually quite surprised that I hadn't come across it before, but I always kind of niggled at the back of my mind why some of the lovely coffee table books, which have zooms into the Mandelbrot and Julia sets, have that detail, but just weren't producing it with the standard algorithm. All the code is online, so you can certainly have a look at that and have a play with it. I've got copies of both the Julia and the Mandelbrot online, so I hope you enjoy that.